So this first theorem is the one that we proved in the last video. This one for sure you need to memorize. Okay? This second one over here, it's worth knowing. It almost never comes up. In fact, in the book problems for your homework, none of them have, not because I didn't pick any, but it just doesn't have this theorem in them. So I would say just memorize the first one. Don't worry about the second one. Okay, so I want to show you a few examples of using that theorem. Basically what we're going to do is we're going to manipulate what we have to look like some form of that. My recommendation for this is to start by trying direct substitution, just like with any non-trig limit. If you plug your number in, does it work? If not, if you have a 0 in the denominator somewhere, then you need to look for a way to get rid of that, okay? By using this theorem or other algebra or trig rules, but we cannot break algebra rules. Okay, so for this first one, we have the limit at 0 of sine of 4x over 3x. If we plug 0 in, we get 0 over 0. We know that means keep going. Now, we cannot cancel the x's out. Don't try it, okay? That's not how trig works. This right here is untouchable unless you want to use like a double angle or identity or something like that, and I kind of doubt you do. So our goal then is to make this look like sine of something over itself. Okay, so to do that, because I have a 3, I want that to be a 4. I'm going to move the 3 to the front, and I'm going to write it as 1/3 times the limit at 0 of sine of 4x over x, and then ask myself, what do I need to put right here in order for this to match this form? Now, yes, I have a 4x there and just a single x there. It doesn't matter as long as I have the same thing in both spots. So for example, if this said sine a over a, or sine 6a over 6a or something like that, then this will work just fine. So to do this, I'm going to multiply by 4 down here. If I multiply by 4 in the denominator, I have to multiply by 4 in the numerator to keep things algebraically balanced, but I'm going to do that over here at the end, and so I'm just going to put times 4. So basically I've multiplied by 4 over 4, but one of these 4s goes inside this fraction and the other one's on the outside. Now this does have a limit at 0. It is equal to 1 according to this theorem. So what I end up with is 1/3 times, and then this limit is 1 times 4, which is 4/3. Okay, let's do another one. Here I have 3x times tangent x over sine x. If I plug in 0, I have 0 times 0 over 0. Doesn't work, so what I'm going to do is I'm going to space this out, break everything into tangent. I'm going to break into sine and cosine. I'm going to write everything as a separate factor and look to see what can be done. So this and the 3 can be factored to the front now or later, doesn't matter. So limit as x approaches 0 of 3 times x. Now tangent is sine over cosine, so I'm going to write this as sine x times 1 over cosine x, just in case I need to put something under there, okay, times another 1 over sine x. Now, here, in this case, I can cancel this sine x and this sine x, and now I have 3 times x divided by cosine. I don't have any problems at 0 anymore. So in this case, I did not have to use the theorem. Just because you see sine doesn't mean you have to use the theorem. In this case, the signs cancel, but I'm going to plug 0 in and have 3 times 0 times 1 over cosine of 0 is 1, so I end up with 0. Okay? For this last one, this one's a little more complicated. I'm going to, I'm going to plug in 0 first, but it's not going to work. So I'm going to write everything in terms of sine and cosine, and I'm going to spread out all of the factors, okay? So I'm going to write this as the limit as, oh, this should be a theta, typo, okay. Limit as theta approaches 0 of 3 times, now cosecant is 1 over sine, so 1 over sine of 2 theta, times cotangent is cosine over sine. Since that's in the denominator, think of it as moving tangent up to the numerator, and then we have sine of 5 theta times 1 over cosine of 5 theta. Okay, now, nothing cancels out. This factor here is not an issue because cosine of theta, or cosine of 0 is 1. Here is where we have the problem. Okay, we have sine of 2 theta in the denominator. Sine of 5 theta, sine of 2 theta are not related. Okay, it is not equal to 5 halves. I can't factor those out or cancel the thetas or anything like that, or cancel the sines. So instead, what I'm going to do is I'm going to multiply the entire fraction by something in the numerator and the denominator in such a way that both of these match this form of the theorem. Okay, so since I have sine of 2 theta here, what I'm going to need to do is multiply by 2 theta in the numerator. Okay, so times 2 theta. All right, and because I've multiplied by, I'm going to put this at the end. Essentially what I'm doing is I'm multiplying by 2 theta over 2 theta. This one is going over here to be in this numerator. This one, if I leave it here, I have a 0 in the denominator, which I don't want. Now, I could put it under this sine of 5 theta, but then the coefficients wouldn't match. So what I'm going to do is, because 2 theta is just 2 times theta, I'm going to take this theta and move it to here. Okay? And now, in order for this to have a limit, I'm going to multiply one more time. And I'm going to multiply by 5 in the denominator, meaning I also need to multiply by 5 in the numerator. Okay, so I've got a lot of factors here, but what I have left is the limit as theta approaches 0. Oh, actually, I don't need the limit anymore because I'm going to evaluate. So I have 3 times, and then this first box matches our limit form, so that's equal to 1, has a limit of 1. This box also has a limit of 1. This is 1 over 1. Here, that 2 got used up. This 2 is left over. So I have a 2 in the denominator, and I have a 5 in the numerator. So I am left with 15 over 2.